Well, thank you very much for that. The lecture is now open for general discussion. I'm going to invite questions. I'd like each of you to give your name and organisation, and there is a roving mic.
Okay, my name is David Cairns. I don't have an organisation for the last 8 years because I've been retired for that length of time. I did work for Scala Business Solutions, and I worked for them back in 1998 when the Millennium Bug was on the horizon. And in order to get there was a problem about the extra size you needed for 8-digit dates. And in order to get the space, they decided that they would cross-compile BASIC, in which the system had been written, and there were 10 years of legacy code in it, if not 20. And they decided they would write it by cross-compiling into C++. And we were going through the testing phase, and one of the well-established routines crashed. So, of course, I get to look at the code. Never looked at it critically before, and I know why it crashed. It crashed because in BASIC, you can jump out of a subroutine, and because the memory model is flat, it doesn't matter. Once in C++, you get Stack Overflow, and that's what was happening. You had to put in umpteen entries before that happened, and we had a very thorough tester who ran it. Now, what I'm saying is, and it's the question, when you're going through the textual analysis of programs in a high-level language, you're going to have to know an awful lot about how those are going to be implemented on the target hardware. And one of the things about high-level languages is that the target hardware is multifarious. The whole idea of high-level languages is that they run on different processors. So how do you cope with that? Do you take the text of the program at face value according to the theoretical model of the program definition, or do you look further down and see how it's going to be running on the hardware?
So basically, what we do, we actually do the analysis on a kind of intermediate language, so that actually looks that has some kind of control flow graph. So it's going to take care about, for example, like jumps and these kind of things. First of all, second, like I think there are like kind of different kind of analysis that one can do all the time, right? So at different kind of levels, you can have it at the level of the source code, but also you can have it at the level of the binary code. That, for example, after the code has been compiled. So for this kind of work, we have been working only at the source level code. But of course, it would be interesting to see if it's possible to actually extend this kind of techniques also for doing it, for example, at binary code.
Hello, my name's Kareem. I'm a student at Imperial College London. So my question is about the to be continued at the end of the lecture. So you've got these tools that scale to basically the biggest code bases that exist. What is next? What do you see is the next big thing on the horizon for?
Well, there are many things that actually we can do. For example, like one thing that is very interesting is like to actually do it for concurrent code, right? So I'm doing some work together with Alistair Donaldson at Imperial College, trying to extend this kind of techniques on concurrent code. But also, I mean, it would be interesting also to have techniques to, for example, to try to understand which kind of, to try to understand better the quality of the results. And other work would be, for example, to extend the model to get many other kind of things. So this direction. But I think like the concurrent one is the most interesting.
Thank you. Another question, please.
Thanks for a wonderful talk. I just wondered the techniques that you've... Oh, sorry, I'm Alistair Donaldson from Imperial College London.
I just mentioned
I wondered, is there any prospect of using the analyses you've developed to help people improve their code in other ways than correctness? So, for example, to optimize their code for performance?
I think yes. I think you can actually use. I think you can use part of this kind of analysis on the shape of the heap in order to help compilers to optimize the kind of to do better optimizations. Absolutely, yeah. And I think Albert will agree with that.
Thank you.
Arend Rensink, University of Twente, Netherlands. At some point you mentioned that your technique is an over-approximation. It was a sound over-approximation. But still it's an approximation, which means that either false positives or false negatives should be possible. Can you tell us which one it is? And is there still something to be gained in that area? You get closer approximations or better ones?
Yes, so of course it's an over-approximation, so what we get is like false positives. So we get false positives because we do over-approximation. And then the question is like how, if we can improve our model in order to reduce the number of false positives first, and also like trying to improve the technique to actually enlarge the kind of proof that we have, so the kind of the code that we can actually prove. But absolutely, it's like the most important thing is like trying to improve the quality on the false positives.
Again, thank you for a fascinating talk. It's a long time since I was actively a computer scientist, but I actually started my IT career at your institution in the computer center many years ago. I would like to ask what is possibly the naive question from somebody, an academic distance away from your work. Obviously, the work that you're doing is based around the development of a software system to do this stuff. How many lines of code, and how have you verified your own code? Do you just pass it through your own tool, and is that an adequate solution to that problem?
Well, the easy answer probably would be that our tool is written in a different language, so we cannot. Well, I mean, the thing is like. What you are proposing is kind of like, okay, we analyze our own tool, and then you actually need to analyze the analyzer and so on and go on. Like we will have kind of a bootstrap kind of problem. But I mean, I think like what you need is like this kind of techniques like just to increase the kind of confidence that you have in your code. So even if like you say like, oh, I'm gonna analyze my analyzer and so on, there are all sorts of things that can happen, like even at a hardware level, that are beyond the control of a certain part of the code. So even if the analyzer would be checked in a formal way, there could be something else that goes wrong. So,
thank you.
Stephen McGibbon from Microsoft. So formal verification, it's very, very interesting. I'm wondering, the flip side of the verification coin is specification. So could your techniques be generalized to help with formal specification from the outset? Well, I mean, this technique kind of synthesizes the specification, so you don't have to write it. So it's done. Well, I mean, what that means is like you can improve it, right? So in certain cases, you will not find all the specification you want, but you will have some initial specification, for example, that try to describe the memory safety, and then maybe you want to have like verification that actually talk about like functional correctness, so you might actually add stuff to that. Some systems you want to start out mathematically specifying. Yeah, but part of this work just generates specifications.
Sean Barker, BAE Systems. I presume because of composability, you could actually verify your program plus the compiler plus all the other parts of the system that go into making the overall physical system, including eventually the processor itself. Is that a fair guess?
Yeah, there's been like some work where people have verified the compiler. I think you can have like the whole chain.
Charles, look, I work for myself. I wondered whether, from your work, you're able to draw any novel conclusions about software design, and if you manage to, do you see a time where better software design would make your work effectively redundant?
I don't think so. No, I think so. I think. Software design is very important. So we need to have like. So I think we need techniques for all the phases of software development, from the design up to the coding.
So if you have a good design, but this is like implemented in the wrong way, then it's not good, right? So you need that techniques that are work for the design, so help you to make a good design, but also you will need technique that help you to see that what you have implemented is a good implementation of your design, right? So, and the work that I'm working on is like for the second part. But absolutely, we need like techniques for every kind of phase.
Hello, my name is Florian Kammeler. I'm from Middlesex University, and I was just wondering if I understood it right, that your technique of abduction somehow makes the properties compositional. Is that correct? Because that, I mean, that there are some properties, in particular in security, which are inherently non-compositional. Or is it a sort of an overstatement of just saying that you actually turn your properties into being generally compositional?
So so abduction worked for us to make it compositional in terms of this kind of property we were looking at. It might be that it could be extended to other kind of techniques, other kind of properties, but I don't know. I mean, I haven't looked at it, so it might be. But I can only say that if you want to do this kind of analysis, it helps to make it compositional.
David Crocker, Escher Technologies Limited. When you're verifying programs which include loops, do you have to generate loop invariants? If so, how do you do it, and what sort of invariants do you generate?
So we don't have to. So the loop invariant is generated automatically. When I show you this technique about the abstraction is the way for the symbolic execution to automatically generate a loop invariant. So it's going to try to compute the loop invariant automatically, and the abstraction is done only for that. So the user doesn't need to specify that. It's automatically computed.
Rich Pilling from Oracle. As my friend from Microsoft would say as well, we have a very large code bases in some of our software. Do you have an upper bound on the sizes of code you can go to, or is 5 to 6 million where you're working at the minute?
So I mean, the last time I saw a benchmark was like 9 million line of code. So.
Holger Hermanns, Saarland University, Saarbrücken, Germany. So Dino, I have a tool that can compete with yours. It can solve problems. It always says "don't know." Now, obviously, it's not a competitor, but still, my question is: don't you need kind of a metric in order to say how good your tool is? How often it says "don't know"? How tight your approximation is? Don't you need something like a measure there? Also, if there are now more that are taking up your ideas and try to compete with you and so on and so on, how can I decide what is a good tool, what is a bad tool? Just being able to process 5 million lines of code is, I think, is not obviously a good result.
Yeah, that's right. So obviously, what is happening here is like we try to have the tool that first is like trying to make pointer safety proofs for as much as code as possible. Okay, and when you have this kind of proof, it tells you like, okay, if you run under this precondition, your tool, your software is not going to crash. So that's the one thing. So it gives you certain kind of information. Second, it's going to find you certain kind of errors where it cannot find the proof. And if I can give you a metric, for example, if I take 3 RTOS, some kind of real-time operating system, and I run the tool at the moment, it will just prove 83% of the code, and then find defect for 3% of the code, and the rest is going to be still, I don't know. So our challenge is like to push the precision of the model such that this 10% left that I don't know is shrink more and more. So and I think it's like something that the more we tune the tool, the more we are going to improve.
Andrew Jones, Imperial College London. Following from your previous answer, do you have any sort of insight as to where these don't knows come from? Is there some common thing that causes your don't know, and that's a big problem you're unable to solve at the moment? Some common cause?
Yeah, I don't know. No, well, actually, so part of the imprecision comes from coarse treatment of arithmetic. So many kind of, I don't know, comes from the fact that we don't know if something is, because we don't count.
You mentioned, or at several points, other programming languages than C were mentioned. And you seem to suggest, when you said that your own tool is not written in C, that if only people would not write programs in C, then all the problems would be gone. I think this is only partially true. So even if I write a program in Java, I can have memory leaks and null pointer dereferences. So do your techniques transpose to other programming languages, and do you actually have experience in applying them there?
So I think the techniques, they are not like really bound to C. So as you said, like you could use it for Java, because in Java you still have this kind of problems, like a null pointer reference. So at the trivial level, they can be used for any kind of programming language that has this kind of problems. Then the implementation we have like works for this particular programming language. It's another story.
Hello, I'm Elena. I'm for personal things here. So, which kind of license do you think you will release this tool, or if it will be available in?
It is released on BSD license.
Thank you. Paul Martinenko, I'd like to invite you to come up now and give a vote of thanks to our speaker, please.
So, ladies and gentlemen, that was a fantastic lecture. It's a topic which I think many of us would be, my computer science goes back 30 years, okay? Proving computer programs then was something people were trying to do. Your approach to decompose, to look at things elegantly and logically, is a really good way of doing things. The prize is enormous, both commercially and for society. Programs that work. Programs that we don't spend hundreds of man-years trying to test. And then we have memory leaks. And anybody who can make the audience laugh on memory leaks and crashes, right, when my life, typically I don't laugh, is someone special. So this is a big prize. As the chairman of the board of professionalism, it's at the heart of what we're trying to do, from the point of view of reliability and predictability. And to do that in the way you're doing it is absolutely amazing. So I'd like to, on behalf of the audience, say thank you very much indeed.